Guys, welcome back to TechDose, and in this video we will look at the minimum total distance traveled problem, which is from Leetcode number 2463, and we will be looking at the optimal solution using recursion and dynamic programming. If you already know how to solve 0-1 knapsack problems, then this problem is going to be easy for you. Otherwise, I will also give the link for watching my video on 0-1 knapsack to learn it. Now let's look at the problem statement. In this problem, there are some robots and factories on the x-axis. You are given an integer array robot, where robot at I is the position of the ith robot. You are also given a 2D integer array factory, where factory at j equals position j and limit j indicates that position j is the position of the jth factory, and the jth factory can repair at most limit j robots. The position of each robots are unique. The positions of each factory are also unique. Note that a robot can be in the same position as a factory initially. All the robots are initially broken. They keep moving in one direction. The direction could be negative or positive direction of the x-axis. When a robot reaches a factory that did not reach its limit, the factory repairs the robot and it stops moving. At any point, you can set the initial direction of moving for some robot. Your target is to minimize the total distance traveled by all the robots. Return the minimum total distance traveled by all the robots. The test cases are generated in such a way that all the robots can be repaired. Now, the conditions to note here are extremely important to solve the problem. Let's look at them one by one. All the robots move at the same speed. If two robots move in the same direction, they will never collide. If two robots move in opposite direction and they meet at some point, then they do not collide. They just cross each other. Okay? If a robot passes by a factory that reached its limit, it crosses as if it does not even exist, because if the factory do not have limit, then it cannot repair the robot, right? So the robot will keep on finding for the next factory. If the robot moved from position x to position y, the distance moved will be absolute value of y minus x. Okay. Now, before looking at an example, let's look at the constraints given. In this problem, you are given 100 robots at max, and the factory's length is also 100, and each of the factory can have a limit value which is equals to the robot's length. That means total factories can be 100 and each of the factory limit can be 100, so it can effectively repair maximum 10 to the power 4 robots, whereas the robots are always less than equals to 100. It is also guaranteed that it will always be possible to repair all the robots. Therefore, you can conclude that the number of factories must always be greater than equals to the number of robots, right? Now, let's look at an example for better understanding. Let's say that we are given some robots R1, R2, R3 and some factories with their respective limits. So they will be given in the robots array as 0, 4, 6, which is R1, R2 and R3, which are the 3 robots, and the positions are given on the number line. If you remember the problem statement, then the position can be from negative to positive, minus 10 to the power 9 to 10 to the power of 9. Here I will just be taking positive numbers. Now the factory array represents each of the factories. So this is F1 and F2. Now in the factory F1, where it is present, the position is given by the first value, and how many robots can it repair, which is the limit value given as the second value. Okay, and the same thing is given for factory 2 as well. So if you notice, you have 3 robots and you have 4 factories in total. So definitely you can repair all the robots, and in the question it was mentioned that it will always be possible to repair all robots. Now, given this information, our goal is to find out the minimum total distance traveled by all the robots so that they can get repaired. So if I assign this R1 to F1, if I assign this R2 to F1, and if I assign this R3 to F1, is it possible? It will not be possible, because R3 cannot be assigned to F1 along with R1, R2, because the limit of F1 is 2. So R3 has to be assigned to the second factory, right? If you do this kind of assignment, then the total distance that R1 has to cover is the gap between F1 and R1, which is the absolute value of the position of F1 minus the position of R1, right? So that is equals to 2. And then R1, F1's gap is also 2. So it has to travel 2 distance to the left. And R3 is at the same position of the factory, so it has to travel 0 distance. So the total distance traveled in this case is 4. Now you can try out other assignments too. You can say that I will assign R1 to F1 and R2 to F2 and R3 to F2 as well. Yes, it is possible. R1 has to still travel 2 units, R2 has to travel 2 units, but on the right hand side, because the gap between 4 and 6 is 2. R3 still do not have to travel anywhere. Okay. Other possible assignments could be R1 being assigned to F2, R2 and R3 getting assigned to F1. But then this does not make sense, right? You will always want robots to go to the nearest factory as much as possible. So in this case, the answer is 4. If you try out, then you will see that there will be multiple assignments which will give you 4 as an answer. But I don't care if there are multiple assignments. I just need to reduce the minimum distance traveled, and I will just return the distance value as an answer. So I hope the problem statement is clear. Now we will look at some observations to build our optimal solution. In this case, the first thing to note is if I have R1 and R2 and F1 and F2 as per the configuration given, then I will never move the R1 to the farther factory and R2 again to the farther factory. It will always be optimal to assign R1 to the nearest factory and R2 also to the nearest factory, isn't it? So if you think you cannot generate any configuration where two robots will collide, the collision case will not happen, okay, because the crisscross movement will not be done. Now, if you take this R1 and R2, then it will be optimal to assign R1 to F1 and R2 to F2 as well, right? It is very logical. Now, let's look at the second point. Since all the factories are identical, therefore, we can simplify this problem by not just including the limit, but then we can include the factory limit number of times. And we can say that we have these many factories. Okay, so the problem will reduce to now assigning the robots to the factory. Instead of assigning the robot to factory and keeping a track of the limiter, like when we are running out of the limit, it will become 0, then we will run out of it. Instead of keeping track of that, since it will be complex, so I will write F1 2 times. That means 2 factory instances are present at position number 2. And if I write in that way, then you will look that R1, R2, R3 are 3 instances of the robot, whereas F1 and F2 are actually the same factory 2 instances, because 2 factories will be added at the same position, and F3, F4 are again 2 factories at 6. Since the problem already mentions that all the factories are identical, so F1, F2, F3, F4 will serve as if they are the same, okay, just that they are present at different positions, and we will no longer be required to maintain the limit value, but we will just be doing simple assignment of robot to the factories. So this is an important observation to make. Now, the third thing is keep the factories and robots sorted by position, because that will make the assignment solution very intuitive. Another observation from the problem constraint was the distance should never be negative. Therefore, we need to take the absolute difference, and that is why it is already mentioned in the question that the gap that any robot needs to travel is always the absolute distance, because if the robot travels to the right hand side and if you subtract 2 and 5, then you will get -3. So always take absolute values, because distance will always be greater than equals to 0, right? Now, having known all these things, our idea of solution will be to try out all the possibility of assignment. Now, what will be all the possibilities? Now, if you try to assign from right to left, then I can assign this R2 to F3, or I may choose not to assign to F3 but to assign to F2, or I may choose not to assign to F2, or I can assign to F1, right? So there will be factory number of times choices for this robot R2. Let's say that R2 has been assigned to F3. I will go with one assignment. Then R1 will have factory -1 number of choices. So R1 can be assigned to either F2, or it cannot be assigned, and it will be assigned to F1, or it cannot be assigned, right? So when you look at any robot, then it can have a choice of all the factories with him, right? And for each of the selection that this robot 2 makes, robot 1 will have n-1 number of choices. So if there are m number of robots and n number of factories, then the total number of combinations that you can generate is 2 to the power of m plus n, because each of the robot can either select a factory or cannot select a factory. And the same thing goes for the factory. A factory can get assigned to R2, or it cannot get assigned to R2 but to somebody else, right? So that will generate 2 to the power m plus n possibilities. Now let's see how this idea works with recursion. Now I will take the problem where I am given the robots and we have 2 robots with position marked as 2, 8, and I will take the factory array where I have 3 factories which I actually have taken in ascending order, because I will be sorting it anyway. So I have the factories at 0, 3 and 6, right? Now in this case, what I want to find is, given 2 robots and 3 factories, what will be the minimum distance traveled by these robots so that they will get repaired by any of these factories, right? So as I discussed in the idea that each of these robots will have their own options, like it will get assigned to either the factory number 2, or it will not get assigned to it. Again, it can get assigned to factory number 1, or it cannot get assigned to it, and again to factory number 0, or do not get assigned to it. So there are two choices for each of the robot for every factory. So in this case, in order to try out all the possibilities from right to left, I will try the assignment of each of the robot with each of the factory using the sub problems. And what is a sub problem in this case? The sub problem is based on which robot I am seeing and which factory I am seeing. Okay. So if I can define a single sub problem, let's say 1, 1. What is the meaning of this 1, 1? The first one is the robot position. This means that I am looking at the robot number 1, and the second one is the factory position. This means I am looking at factory number 1. So the answer given by this sub problem 1, 1 will be equals to, if I had these two robots and these two factories, then what will be the minimum distance that these two robots will have to travel in order to get it fixed. If it is not possible to be fixed, then I have to return an infinity value. Otherwise, if it is possible to be fixed, then I will return the integer value for that. Okay. Again, I will take another example to explain the sub problem. Let's say if I say, what is the meaning of the sub problem 0, 2? So if I write 0, 2, then I am looking at this robot number 0 and I am looking at this factory number 2. This means that if I just have one robot and two factories, then the answer returned by this subproblem 0, 2 will mean what will be the minimum distance traveled by this robot number 0 and all these given robots on the left hand side, so as to repair them all having 3 factories at our disposal. Okay. Now having known this, let's try to process this using the recursion approach. So in this case, I will be starting at this point. This will be a robot position which is 1 and the factory position which is 2. And I will always have two options, whether this factory will be assigned to the robot or it will not get assigned. So the first possibility is not getting assigned, and the second possibility will be this factory gets assigned. So let's say that I try the first possibility, that the robot will not be assigned to factory number 2. So if it is not assigned, then we will be going back to the other factory, that means factory number 1. But the same robot, since it is not assigned, it will we will try with the same robot. Okay. So from 1, 2, we will be going to the subproblem 1, 1. Right. Again, being at 1, 1, robot number 1 may or may not be assigned to factory number 1. So if we do not assign it to factory number 1, then we will go back to factory number 0, that means 1, 0. Otherwise, if I try to assign it, then we will go to 0, 0, right? Now let's say that I go with the non-assignment approach and I will be moving to 1, 0. So currently I am at factory number 0. Again, we will have two possibilities, whether this robot 1 be assigned to factory 0 or it is not assigned. So if I do not assign, then I will go to 1, -1. And if I assign, then I will go to 0, -1, right? So these are the two possibilities again. So if you look at it, when you go to -1, then actually you have run out of the factories. So if you have run out of the factories, you should also run out of the robots, because according to the problem statement, all the robots must be repaired. You see that I still have a robot. I have actually two robots, right? One means I am looking at robot number 1, which means two robots. So it is not possible to actually repair all the robots. So you have to return an infinity from here. Okay. So this is the base case where you go to a negative index in factory. We have to return infinity. From the other side, in the include case, if you look at it, I am looking at robot number 0. That means I have one robot, but I am looking at factory number -1, which means there is no factory. We are out of bound. So here as well, we have to return an infinity. Now what should this subproblem 1, 0 return? 1, 0 means I had one robot at my disposal and 0 number factory. That means only one factory, right? So what should this return? Since I tried both the possibility of including or not including, therefore excluding whatever was my subproblem result will come on one side. And if you had done this robot 1 assignment to factory number 0, then what would be the movement that you have to do? That will be the absolute value of Ri minus Fj. That means the position of the robot minus the factory position, which will be 8 minus 0 absolute value will be 8, plus whatever you get from the sub problem, that has to be added. So this will be infinity. And since we want to minimize the distance traveled, I will be using the min function. So this min of infinity comma 8 plus infinity will be equals to infinity. So this will be returning an infinite value. Okay. Now this 1 comma 1 sub problem got infinite value from the left hand side. Now when I try to assign this robot number 1 to factory number 1, then what will happen? Then actually we have to add the distance, right? What is the distance traveled if you have to repair robot number 1 with factory number 1? It is the gap, which is 8 minus 3 absolute. So this will be 5 plus. Now we will go to the sub problem, which is 0. Since this robot has been assigned, I will go to robot number 0. And since this factory is done, I will be going to the next factory, which is factory number 0 as well. Again from here, I will try out the two possibilities, that either this factory be assigned or not be assigned to the given robot. So if you do not assign this factory, then you will go to the sub problem of 0 comma minus 1. Here minus 1 indicates you have run out of factory, and 0 means you still have robot number 0 with you, right? So this will return infinity, since you could not repair all the robots and you have run out of the factories. And on the other side, if you want to assign this robot number 0 with the factory number 0, the distance traveled will be 2 plus, because 2 is the gap between robot 0 and the factory 0 positions, right? 2 minus 0 plus, what is the return value from minus 1 minus 1? Minus 1 indicate that you have run out of the robots as well as you have run out of the factory. So if you have run out of the robot, that means that all the robots have been repaired, and in that case you have to return a 0 value. That means you do not need to travel anymore because all the robots are done, right? So there should be always a check for the robots position first before checking for the factory position, right? So if the position of robot is minus 1, then that means I will always return 0. I don't care if I have a factory or I don't have a factory, right? So this will return 0. Now it already got infinity from the left hand side. It will take the min of these two values and it will return 2. Now this 1 comma 1 will get 2 after including it. So what it will return? It will return the minimum of infinity comma 5 plus 2, that means 7. So if I look at the entire problem, because if I have 2 robots, that means I am at robot position number 1, and I have 3 factories, that means I am at factory position number 2. This is the main problem, right? All the rest of them are the sub problems. So if I decided to exclude factory number 2, that means robot 1 will not be assigned to factory 2. I got an answer of 7. Okay. And since I will be minimizing all these values, I have to calculate if I do the assignment of robot 1 with factory 2, then what happens? If I do this assignment, the gap between them 8 minus 6 is equals to 2 plus. I will be making the call to this sub problem. That means if I do this assignment of robot 1 with the factory 2, then I will be moving back on the robot and I will be moving back on the factory. So I'll be going to 0 comma 1 from 1 comma 2. Now at 0 comma 1, again I will try to assign this 0th robot to the first factory, or I will not assign it. So if I choose not to assign, then I will move back in the factory, but I will remain at the same position in the robots, right? Now if you look at it, then this sub problem had already occurred. So this is a repeating sub problem. We don't need to solve this, while just by doing by recursion you have to solve. So I know that if I calculate this, then I will get the same answer. So I'm just skipping this step and I will be returning a value equals to 2. Okay, because the 0 comma 0 had returned 2. So 2 I got from the exclusion case. If you try to include, that means make this 0th robot assignment to the first factory, then the gap between them 3 minus 2 is equals to 1 plus. When I go to this sub problem, then I see that the robot position is negative. This means all the robots have been repaired, and in that case you need to return a 0. So 0 will be returned, and since I want to minimize the distance, I will take the minimum of both the cases. So 2 comma 1 will be returning a 1 here, right? So if you get a 1 here, then 1 will get added, and since I want to minimize the distance, that will be equals to 3. So by traveling 3 distance in total, we can assign all these robots to the factories and get all the robots repaired. And that assignment will be 2 will be going to 3 and cover a distance 1, and 8 will be going to 6 and cover a distance 2. So that will be equals to 3, right? So I hope you understood the recursion approach. Now in this case, we know that there are repeating sub problems. This is a small example, so it is not very prominent. But if you take a larger example, you will see that a lot of repeating sub problems will come. And since there are repeating subproblems, it is always recommended that we remember the solution of the subproblem when we solve it the first time, and then we return it as long as we keep on seeing that same subproblem, right? But if you solve it by recursion, then since you know that there are total of 2 to the power m plus n number of subproblems by trying out all possibilities, therefore you will get the same time complexity as 2 to the power m plus n, right? So that will be order of 2 to the power m plus n. The space complexity will be the depth of the call stack, since we will be using recursion in this, and the depth can go to m plus n, because at every level you will either assign a robot to a factory or you will be skipping the factory simply, right? So your depth cannot go to more than m plus n. So the space complexity will be order of m plus n if you solve by recursion. Now in this case, if you look at all the subproblems that can be created, then the subproblems depend on the robot position and the factory position. So if you want to see all the combinations, then you have to multiply them both. That means if the size of the robots is m and the size of the factories are n, then the total number of combinations of subproblems will be m times n, right? So can we generate these many subproblems? In this case, if you look at the robot, then the robot positions can go to 0 and 1. And if you look at the factory positions can go from 0 to 2, because we have 3 factories, right? So what I can do is, this will be showing me all possible subproblems, right? So this I can call as the memoization 2-dimensional table, which will be of size m by n. And whenever I calculate an answer, then I can save it here. So while doing the recursion call, if I had calculated the answer for this 0, 0 as x, then I will be returning the same answer when I see this 0, 0. I will pre-fill all these values with -1, indicating that it has not been calculated. Why with -1? Because the distance values cannot be negative in this case. So I will fill it with any negative value, and that can never occur. So if I see a -1 in the memoization table, then that will mean that this value has not been calculated, right? So if I happen to see a non-negative value, that means some positive value, it is already calculated, and we will return the value having known that x was the result at 0, 0. As I saw, 2 was the result here, right? So I can say what 2 and return it back without having to solve the subtree. So with this approach, since we are solving each of the subproblem exactly once, and when we see it the next time, I will just be returning back the answer instead of solving it again, right? So each of the subproblem will be solved exactly one time, and that is why the time complexity will be order of mn. And we have taken the memoization table, which will be of space complexity order of mn, right? If I can give you a brief about the time complexity, then recursion took order of 2 to the power m plus n and space complexity order of m plus n, while the DP will take more space complexity, which is order of mn due to the memoization table, while the time complexity will be significantly lower, order of mn, where m is the number of robots and n is the total number of factories, which we had calculated after multiplying the factory with its limiter, right? So if a factory had limit as 3, then I will be including 3 instances of that factory at the same position. So when we do that, after that we take the value of n. The maximum number of robots was 10 to the power of 2, and the maximum number of factories was also 10 to the power of 2, but then the limit per factory was also 10 to the power of 2, and therefore the n value can go to maximum of 10 to the power of 4. And since this is an mn algorithm, so this will be having 10 to the power 6 computations, 10 to the power 4 multiplied by 10 to the power of 2, and this is less than 10 to the power of 8, so this will definitely run within 1 second, and this is the optimal approach. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code, I have defined infinity with a very large value. Okay, so this is a long 64-bit integer, very high value, which will not occur in any of the distances. If you look at the main function, minimum total distance, then here we are given the robots with all its position and the factory with their respective position and the limit values. So first thing which I do is I will be sorting the robots and factory, as I said, and then I will be extracting each of the factory instances by repeating it limit number of times. So if a factory is at position 2 and it is having a limit of 3, then I will write that there are 3 factories at position 2. okay, so that I can easily solve it with the include and exclude logic. After this, I will be taking the memoization table just to store the solutions of each of the unique subproblems so that I don't have to repeat it again. And I will be calling the min cost recursive function. Here I will be sending the robots array as well as the factories array, and the robot position, which will be the last index of the robot initially, and the factory position, which will be the last position of the factory array. And this is the memoization table. The first thing I check is if the robot position is less than 0, because if it is less than 0, I don't care if factory position is less than 0 or not. This means that I have assigned all the robots, and that is fine. So that is why I will have no further assignment, so I will be returning 0. But if the robot position is greater than equals to 0, that means we still have some robots to be assigned, but we run out of factories. That means factory position is less than 0. Then we will be saying infinity. That means the robots can no more be assigned. Okay, that all the robots cannot be repaired. Now, after having checked the base cases, we will be checking if we have already seen this subproblem. If yes, then the value at that position will not be a negative value, and we will be returning whatever was the value calculated initially, right? Otherwise, if this subproblem is seen for the first time, then we will be trying to do the assignment of the current robot to the given factory, and then I will be adding the distance value, what was the gap. To this, I will be calling the subproblem where I will be going to the previous robot position and I will be going to the previous factory position, because the current robot position is assigned to the current factory position, right? And the other case was the exclude case, where I will choose not to assign the factory to the given robot, but instead I will just skip the factory and go to the previous factory, right? So out of both these scenarios, since I want to minimize my distance, so I'll be assigning a min function to include and exclude, and before returning back, I will be saving the subproblem result into my memoization subproblem matrix. Okay, so this is the entire solution, and I hope you were able to understand it. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.